yeah, okay. I was like, am I like late? And I checked my thing. I was like, no. Oh, this room actually has like a face cam.
Well, it's not going to be shown.
Okay.
It's more of like a backup.
It's fantastic.
And you have the microphone and everything.
Yeah,
All right,
got
cool.
it set up.
Okay. Well, just call if you need anything.
Okay.
So you're testing the...
Yeah.
Okay, so can you hear me through the live stream?
Well, that's what I'm trying to...
Yeah, I'm just like talking. Yeah, so you can...
Because there's like a delay here.
Okay, yeah, I'm just going to keep talking to see if you can hear me. Let me know if you can. If you can't, that's a problem.
We've already got 8 people.
Is it live?
Yeah.
Oh, okay.
I put it live.
Okay. People are probably like, why is she testing? Hi, viewers at home. Welcome. We'll get started in like 5 minutes when we get the microphone situated.
Alright, just keep talking and doing your thing, because it's like a little bit delayed.
Okay, sounds good. So, just want me to keep talking out here?
Well, I mean, I'll
Okay, you'll...
catch up eventually, so you can.
Okay, cool. I don't want to just like talk to myself. It is.
Oh, like, I meant, like, you're, like, cooking.
Oh. Yeah, I got it. Got you. Thank you. Okay, you guys, so we're going to go ahead and get started. So whether you're here for Dr. Hashim's organic chemistry class or if you're here for another organic chemistry class, my name is Holly. I am the SI leader for Dr. Hashim's class, but this is an overview of just organic chemistry in general for anybody taking a final exam. So this was up earlier, and it'll also be up at the end. So at the end, I'll put up again, and I'll please ask you to, scan the little code. They want feedback on study union, how to improve things, stuff like that. So that's like a logistical thing just to let you guys know. But we're going to go ahead and get started. I had this practice exam put up on my Google site as well as the study union site. So that's where you should have downloaded it from. If you didn't download it, feel free to log on to that site right now so you can follow along. So I'm just going to be going basically straight through this exam review. You can stop me at any point to ask a question. I'm really fine with that. But don't raise your hand, just like yell my name or just be like, hey, you, because I'll be looking down majority of the time. So if you're raising your hand, I don't want you raising your hand for like 10 hours and I'm not going to see it. Some questions I will go through faster than others because a lot of this should be review for us. So yeah, just if you need me to slow down on something, let me know. Any questions that we do not actually finish, I will be at least giving you guys the answers to them so you can understand them later. But hopefully we should be able to get through everything. So we're just going to go ahead and get started. So for number one says, what is the hybridization and the geometrical shape around the nitrogen in the following molecule? So the thing for us to note is that this nitrogen, it has a lone pair of electrons that's not seen on the structure, but because the nitrogen had no positive or negative charge, we should know that it has that extra 2 electrons on there to give it its original 5. So it has 1, 2, 3 electron groups. So because it has 3 electron groups, that would give us the electron geometry, but we're again looking for the geometrical shape. So its electron geometry is going to be trigonal planar, but because only 2 of these contain atoms, the geometrical shape for us is going to be bent. And so our choices then lie between B and D for bent. And for the hybridization, we should see that the hybridization is going to be sp2 because it has 1, 2, 3 unhybridized, and then the only 3 hybridized orbitals, and the pi bond needs the p. So if we have sp, p, p, those are our 3 p orbitals, 1 s orbital. We need one of those p orbitals left alone so we can make the double bond, which means we're going to use these 3 to hybridize, so we're going to get sp2. Mm-hmm.
So I thought for nitrogen it has 2 electrons.
So nitrogen, okay, good question. So nitrogen, we could think it has 2 lone pairs, but remember nitrogen is in that 5th column, so it's going to start with 5 electrons around it, and its valence shell is going to have 5. So it's sharing 1 electron here, 1 electron here, and 1 in the pi bond, so that's 3 of its original. So it only has 1 lone pair to give it its total of 5 to start with. So yeah. Mm-hmm.
I would be confused in terms of the localized and delocalized electrons and then the hybridization. Can you kind of just, I know that's very
Okay, so the whole idea of localized versus delocalized, it does come into play a little bit with nitrogen. But as far as this exam is going to be concerned, you're really not going to have a lot that's going to be trying to trick you on that. You might have one question, if any, on hybridization. But if they were delocalized, we wouldn't be counting them. But they are right here on this nitrogen. I don't want to go too far into it because you're going to learn more about nitrogen being delocalized in an aromatic ring when you get to organic 2. That's like an entire chapter. So I'll wait till then. What we should just pick up from just basic Chem 1 is that it did have 2 here because its starting should be 5 valence electrons, and then we're counting the electron domains to find the geometrical shape. Okay, guys? So for this one, we would go with D. Then we're going to go to number 2. So number 2 says, which of the following compounds is a cis isomer? So we have cis and trans. So before we even start looking at cis versus trans, the first thing that we should look at is, can we name cis and trans? And one of the rules we have is that we cannot name something cis or trans if it has 2 like groups on the same carbon. So taking A, for instance, this carbon has an ethyl going up and an ethyl going down. So we cannot even name that cis or trans. So that eliminates this choice automatically. It also eliminates C because we have 2 methyls on the same side. And it also eliminates D because we have 2 methyls on the same side. So our only possible choice would have been B. B is cis because it has 2 like groups, in this case the hydrogens, going up. Another way we could have named this would be using the EZ method. So look for questions that involve EZ or cis and trans. Okay, so then we're here on number 3. Number 3 says the nitrogen atom, which one has the largest possible formal charge? So we want the largest positive formal charge for this one. So if we're looking at all of these, we said that nitrogen originally has 5 in its valence shell. So its formal charge is going to go with whether it's gaining 1 and having 6 valence electrons, or if it's losing 1 and it's left with 4. So we look here, it has 1, 2, 3 bonds and 2 lone electrons, which gives it 5. It should have 5, so we have a 0 formal charge here. We go over here, 1, 2, 3, 4 lone electrons plus 2 bonds is 6. So that's 1 more than we need. So that gives us a -1 charge, because remember, electrons are negative. We get to C, and this nitrogen, all it has is 4 bonds around it. When it has 4 bonds around it, it's not going to have a lone 5th electron sitting by itself. That would be a radical. So we know this one is missing 1 electron, which gives it a +1 charge. And then we can look here, we have 3 plus 2 is going to be 5, so we have our normal amount, which is 0. So we'd go with C for the largest positive formal charge. Okay? Which of the following compounds is not a structural isomer of cyclohexanol? So one of the first things to remember is that if we're having a structural isomer, it's going to have the exact same number of carbons, hydrogens, and oxygens. Okay? And so we need to look at the degrees of unsaturation to figure this one out. So if we were to draw cyclohexanol, it looks like this. This is what our cyclohexanol should look like. So we have 6 carbons, however many hydrogens, let's see, 2, 4, 6, 8, 10, 12 hydrogens, and 1 oxygen. The main thing to note here is we have 1 degree of unsaturation because we have the ring. If we look at option A, it's identical except it's added a double bond. By adding that double bond, we've eliminated 2 of our hydrogens. So this one cannot be a structural isomer because it's not going to have this same formula. So A, if you did B, C, and D and counted them all up, you'd see that they have the exact same number of carbons, hydrogens, and oxygens as cyclohexanol. All right? And then, what class of compounds does the following structure belong to? So we should be able to easily spot this one. This should be like a good point for us to get on our exam. This is going to be an ester. Okay, so it's an ester because we have a carbonyl attached to an oxygen, which is attached to a regular carbon. I like to think of the word ester as being synonymous to the word sister, because we have 2 sister oxygens right next to each other, 1 in a carbonyl, 1 just right next to its sister. Okay, ether would be this if this carbonyl was missing and it was just an ROR. That would be our ether. Our ketone should just look like a regular carbonyl with 2 carbons on each side. And our aldehyde should look like this. All right? If these are things you're struggling with, they're really easy points to get on this final exam, and there's probably going to be at least 1 or 2. So I'd make sure you know them. Also, for anyone that is in Dr. Hashim specifically, she was talking to me, and she said that a lot of her questions are going to be words, not pictures. So she's going to ask you to make a 3-carbon aldehyde from this. So even though it's multiple choice synthesis, if she tells you you have butane and she wants you to make a 3-carbon aldehyde from butane and you don't know what an aldehyde is, that's going to make it really hard for you to do that question. So knowing these functional groups is really important, and it's even more important when you move on to organic 2. Okay? Moving on. Let's go up here to number 6. So number 6 says, how many sigma bonds are present in the following molecule? So we should realize that when it comes to sigma versus pi bonds, sigma bonds are going to be our original single bond, and then when we're making doubles and triples, we're adding pi bonds to each side. So whether it's a double bond, a triple bond, or a single bond, we're going to count it as just one sigma. So I have 1, 2, 3, 4, 5, 6 sigma bonds in my ring. 7, 8 to connect to this alcohol group. We should know that the OH is actually connected like that. So we have 9. So 9 is all we can visually see, but we need to make sure we are counting all of the hydrogens that are hidden on these carbons. So there's 2 hydrogens here, so we're at 8 total. We have 9, 10, 11, 12, 13, 14, 15, 16, what am I missing? Oh, wait, sorry, 16, 17, what am I doing? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. There should be 18 on here, so I don't know where I'm miscounting right now, but there should be 18. Yeah, so just for this one, no, there's 18. I'm counting 17 right now, but I know I'm mismarking something at the moment. So, yeah, something's being mismarked right now. So if we have time, we'll go back to this and I'll recount them all, but there should be 18 on here. So. Okay, okay. Drew it right, counted wrong. I'm not a math major. So, all right, so we're good here. Let's go to 7. So 7, what direction is the dipole moment of this molecule? Okay, so first of all, something that I don't particularly like about this question, but I still include this question. I don't like the way the question is drawn, like the way the structure is drawn, because it's drawn linear. We should know that molecules are not going to be linear unless it's a triple bond. However, for the purposes of this question, we are going to consider it a linear molecule. So if we're considering it linear, we need to know which atoms are more electronegative than other atoms, because that's going to determine the pull of the dipole. So oxygen is our most electronegative, followed by nitrogen, followed by carbon. So the pull is going to go in this direction towards the more electronegative atoms, which are nitrogen and oxygen. So we would go with A for our dipole moment. All right. Then we're going to move on to 8. Which of the following functional groups is not present in the following molecule? So we look here. Secondary alcohol, we do have an alcohol group. It is on a secondary carbon. So this one is good. So this one is present because we're looking for not. Alkene, that should represent a double bond, which we have. And then we're stuck between ester and ether. I said before that the ester is those oxygen sisters, a carbonyl and an oxygen immediately to one side, which we have. So the ether is what's missing from here. Okay, so for like primary, secondary, and tertiary, or first degree, second, yeah. It's just a different way of writing it. Yeah, sorry, just vernacular. Okay, and then we have number 9, which is what is the name of the following compound? So this is us naming bicyclic compounds. So something we should know is that we always start at the bridgehead, and we're going to go to the bigger side. So luckily for us, all of our options give us the same numbers in the bracket, which in one way is nice, but then another way isn't as nice because we don't have, easy ways to cross things out. But we should know that if we're starting at the bridgehead, we're going to start at the bridgehead that has a substituent, because if we can make a substituent on the first carbon, that's going to be better for us because we always want the lowest numbers. So that gets rid of C and D. And so then our options are A and B. And so for option A, it has us going to the left and going around the big chain first, and option B has us going to the right. Although we might be tempted to go to the right to make all of our substituents have the lowest number possible, we need to remember that for bicyclic structures, we have to go to the bigger side of the ring first. So we're going to go with A because we're required to go to the bigger side of the ring before going to the smaller side. Mm-hmm. If they're the same, okay, good question. So if we had two rings that were the same size, so if these were both four-sided, 4 pieces, then we would go and want to make the lowest number for our substituents. So in that case, we would go to the side that had substituents. But because they're not the same, we have to go to the bigger one first. Good question. All right. So then we go up here to number 10. 10, yep. We go here to number 10, and number 10 says, which of the following is an alkyl acetylene? All right, so this is a little bit, I guess, something maybe you guys aren't familiar with, but something that you guys are going to have to get used to in organic too is you're going to start using common naming system along with the IUPAC system. So acetylene is the common name for a triple bond. So this is our alkyl acetylene, so it's C. Just something to remember. I know it's not going to be on your final exam because it's not written, at least for Dr. Hashim's class, but this should really be straight out because we should know that triple bonds have to be linear. So it's bent and shouldn't be like that because it's a triple bond, but we are going to go with C for that answer. That's just a definition question. Okay? What is the IUPAC name of the compound shown? So whenever we're doing any of these naming, the first thing for us to do is to count the number of carbons in the longest chain because that's going to be our parent. So I can start from either side to begin with. So I'm just going to do 1, 2, 3, 4, and then 5, 6, 7. So 7 is my longest. So I can immediately get rid of option D because it says hexane, which is a 6-membered chain. And then we have to decide if we're going from the right or the left, but like I said before, we're trying to get the lowest number on our substituents. So if we go from this side on the left, we can get 1, 2, 3, and 4. So we're going to have a methyl on the 2 and an ethyl on the 4. And so we want to do that, so it's going to get rid of option C because that has the methyl on the 6. However, then we're stuck between these two, and we should remember that when we're naming, we're putting our substituents in alphabetical order as opposed to numerical order. So we're going to want to put the ethyl first. So 4-ethyl 2-methylheptane is going to be the name of that compound. All right, everybody's favorite chair conformations. So which of the following would be the most stable chair conformation for trans-4-tert-butyl cyclohexanol? So something for us to remember here is, even though for chair conformations, we should all know that the most stable group is what? Axial or equatorial? Equatorial, yeah. So equatorial is going to be better for us, but depending on if our actual compound is cis or trans and where our substituents are located, we might not be able to get both on equatorial. So don't just grab that as your first answer, okay? So if I draw this out as just a regular ring structure, and I'm going to use wedges, I'm going to have my alcohol on my 1 because it's cyclohexanol. And so when it's cyclohexanol, we know the alcohol group is on the first carbon. And then 2, 3, 4, it's trans, so I have a tert-butyl group on a dash. So if I transform this into a chair structure, this is my first carbon, so our wedges and our dashes are what's going to tell us up or down. So if I put my wedge as up right now over here, it means that when I do my dash, it needs to be in the down position, but I'm not going to know if it's equatorial or axial until I write it. So I'm going to go 2, 3, 4. It needs to go down in this particular position. The only way we can go down is to do axial down. So we're going to do our tert-butyl in the axial. So we have both of these in the axial position, but that's not going to be the most stable. The most stable would be if the chair flipped and put both of them into equatorial positions. So in this case, we can, in fact, have both groups in the equatorial. So we would go with A. Now, if instead on this problem we had been given cis for tert-butyl cyclohexanol, and we had to only put one of them in the equatorial and the other one was forced to be in the axial, which one would we want to keep in the equatorial? Yeah, tert-butyl. We'd want to keep the bigger one in the equatorial position. So that's something to keep in mind. A lot of professors like using cis just because it causes you to have to do that a lot. All right. 13. What would you use to carry out the following transformation? So I know that you guys haven't seen maybe all of these reactants. That's going to be something that you guys are going to come into contact with when you do the ACS at the end of Organic 2. But it's okay that we haven't officially studied all of the reactants because we should be able to do process of elimination to figure out our answer. So if we want to take this bromine and exchange it for a hydrogen, we should know that that's not going to work with Br2 in light because that's how we add bromines. We should realize that these are the reactants that we use to form triple bonds. So that's not going to work. We haven't really seen this one, so we're going to skip it. And then we look here, and we have H2 and palladium. And so a lot of us are going to be really tempted to be like, okay, I don't know what option C is, but H2 and palladium, I know that adds hydrogens. However, remember, we have to remember what our starting material is. So it does you no good to memorize all of the reactions for the exam if you only know that H2 and palladium adds hydrogens, but you don't know what your starting material needs to be. So for this, we would need to start with a double bond or a triple bond because these reactants react with pi bonds. So this cannot work because we're starting with an alkyl bromide. We're not starting with anything containing pi bonds. So we have to come to the conclusion that zinc and hydrochloric acid must exchange the bromine for a hydrogen. Okay? All right. We can go ahead and look at number 14. So 14 is, what is the IUPAC name for the compound shown below? All right, so we are just taking a 6-membered ring and drawing it like a normal ring first. So this is axial up, so this is being drawn as equatorial down for this alcohol group because this is up, so this must be down. So we'll put this down one as a dash. And immediately next door to it, there is an isopropyl group, and that isopropyl group is going equatorial up. So it's going up, so it's going to be on a wedge. So then we look here, and we have to look for our naming. So first of all, we should see we have a wedge and a dash, so that's going to give us trans. So we can get rid of options B and D because they're involving cis. So then we're looking between trans 1 isopropyl and trans 2 isopropyl. We should know that the alcohol is going to take priority because it just has, that's how we're doing our priorities. It's going to have the priority. It's actually going to become part of the main name and become cyclohexanol. So the alcohol group in this case is going to take the 1 position, which means we have to go with C because option A gives the isopropyl the 1 position. Okay. All right. This one here. All right, this one says, which of the following show 1-bromo, 2-iodoethane in the most stable conformation? All right, so we could go ahead and put this into the the Newman projection? Newman, yeah, Newman-Fisher. It'll get a little confusing, but the Newman projection, so the one with the circle and looking down the eye of a bond, we can go ahead and do that if we would like to. However, We can also visually, from the way they've given it to us, we can determine which one's the most stable. Because even when we're drawing our Newman projection, we know that we want the bromine and the iodine, because everything else is hydrogen. So our two biggest groups, we want them to be completely opposite of each other. So when we look here, we have a bromine that's going straight up and an iodine that's going into the page, but it's still kind of going up. So they're still close to each other. And then we're going to have over here on B, we have bromine going down and out of the page, and iodine is going up and into the page. So they are completely across from each other if we draw it as a Newman projection. So this one's going to wind up being our answer. We could go ahead and look here too, and this one is not going to be as stable because it's not 100% across from each other. And then D has them also not 100% across from each other. This one, it is our Newman projection. If we were looking from this direction, our Newman projection would look like this. For B. Mm-hmm. Yeah, so D has them at a smaller angle together because we have our bromine sticking straight up, and then the hydrogen for the other one is also sticking straight up, so that's our eclipsed, where they're going to be like overlapping. Yeah. So B is the one that gets them as far apart as possible. All right. 16, what is the name of the following compound? So something that I like to do when I'm told what's the name of the following compound is I like to look in the answer choices and say, okay, what can I eliminate based on just looking at the structure? So the first thing I see is I see that 2 of my answers involve classifying it as cis. So I say, okay, let me make sure, is my double bond actually cis? Because if it is, I can eliminate things that don't include that in the name. I didn't notice. Okay, well, she's going to get that fixed. We're going to go ahead and, okay, so. Two carbons. So it's going to look like that. Okay, cool. Yeah. So it should look like that. And so then it asks us, wants to know something about this final product. These first two say cis and trans, but we should know by having two methyl groups on the same carbon, we can't designate cis and trans, so that is out of the running. And then between tri and tetra substituted, we have three groups, so we are tri-substituted for this double bond. Okay? All right. So number 29. 29 says, what is the correct name for the following compound? So something we can do right away. Okay, we're arcing now, that's good. Okay, so something for us to know about these answer choices is that they all include E and Z, which is great for us because we can eliminate two right off the bat. So we're going to look in E and Z, we're going to look for our highest priority group on each side. So on this right side, our chlorine is our high priority. Sorry, on our left side. Chlorine's the highest priority, and on the right, this isopropyl, of course, is our highest priority because the other one's the hydrogen. So they are not on the same side. They are on opposite sides of each other, so they are going to be E. So we can automatically get rid of options A and C. And then when it comes down to it, we have to look and say, okay, the differences here are not about the parent chain, it's about the numbering. So we're either going to count 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. And we should know that not only do we want our substituents to have the lowest number, the key here is that we want our double bond to have the lowest number possible. So we want our double bond to be 2 pentene, 1, 2, which means we're going to go with 2-chloro, 4-methyl, 2-pentene. Okay. All right. 30. Dehydrohalogenation reactions usually give the most stable alkene as their major product when more than one product is possible. An exception to this rule is when which of the following reagents is employed. Okay, so we should know dehydrohalogenation. Let's break it down. So D, so we're taking things away. Hydrohalogenation. So we're going to be taking away a halogen and we're going to be taking away a hydrogen. Hydrohalogenation. So this is when we're just removing a halogen and we're making a double bond. So that can be when we're using Naomi, when we're using terbutoxide, all those reagents that we've learned. So it says it goes to the most stable, but the exception is when we're using which one? Our exception, we should know that if we use Naomi or NOET, those ones are going to go to the more substituted side. But terbutoxide is so bulky that it's going to make the less substituted. So potassium terbutoxide is going to be our answer for this one. All of these other ones are small or they're not involved in this reaction, so we know those can't be it. Okay? Going up to, we're down to 31. So 31. Which of the following alcohols will dehydrate most rapidly with sulfuric acid and heat? All right, so which of the following will dehydrate fastest? We should know that when we're looking at the sulfuric acid and heat reaction, I know that in Organic 1, for people that are in Dr. Stream, you didn't necessarily have to know all the mechanisms, but she did tell you guys that it's going to be a good idea to know those mechanisms. All right? So if we know what's going on when we use concentrated H2SO4 in heat, we should know that that's actually going to go by as an SN1 reaction, okay? So it's going to go by as an SN1 reaction. So as an SN1 reaction, it's going to happen most rapidly when it's on the preferred carbon. And our preferred carbon for SN1 reactions is going to be tertiary. So B is on secondary, just like D is. C is a primary alcohol. So A, our tertiary alcohol, is going to react most rapidly. Okay. And then, what is the major organic product of the following reaction? So for this reaction, we are using 2 moles of HBr. We're not using HBr and peroxide, we're using HBr, so we should realize that when we do HBr reactions with pi bonds, our bromine is going to go to the more substituted side. We happen to be using 2, which means it's just going to go to the more substituted side twice. So we're going to have it go over here and over here when it reacts, and our 2 hydrogens are going to come to this side. So what we should wind up with is we should wind up with that same methyl group here. We should have Br2 and then CH3. Or if we wanted to draw it out, we would have a methyl here, our 2 bromines go to this one, and then our other one. So whether you drew it as a line or you drew it out as a name, I did it this way because we need it that way to find our answer, which in fact is going to be D. C would be doing the wrong one, it'd be doing peroxide, and then these 2 ones are going to do things that actually can't happen because they're putting it multiple carbons away. So we want to go with D. All right, going down to 33. So 33 says, what reagents would you use to carry out the following reaction? All right. So first thing we should notice is that we're doing a syndiol. We're making a syndiol in this reaction. So in your book, you're given 2 ways to make a syndiol from a double bond and only 1 way to make an anti. Okay? But the important thing for us to look at is all of our choices. So we've seen KMNO4 before, and we've also seen these 2 before. So ozonalysis involves ozone or O3. We're not going to be using ozonalysis because we do that to make carbonyl groups, which we're not doing. So we can immediately eliminate D. We look at C. C is a peroxy acid. When you see this group, CO3H, that is a peroxy acid. A peroxy acid looks like this because we have the carbonyl OH, which is the acid, but there's 2 O's, and 2 O's connected to each other makes the peroxy part, like hydrogen peroxide. So that's our peroxy acid. We should remember that our peroxy acid, the one that's common, is going to be MCPBA. We already know that that one we use to make the antidiol. So we're not going to use C because it makes the antidiol. So then we're between A and B, and the thing that's important to note is that in order to make a syndiol, we have to have KMNO4 cold and dilute. Your book specifies cold for a reason. Putting it in hot with that hydroxide is going to be a completely different reaction. So cold is specific here, and we need to make sure we account for that. Okay? And then for anybody that doesn't know what, I know that some of us have just kind of memorized, MCPBA goes with making the antidiol, and we also know that MCPBA can be used to make the epoxide group, right? So I said that this is a peroxy acid, which is why it makes the epoxide and then goes on to make the anti-diol. But for those of us that don't know what MCPBA stands for, it stands for metachloroperoxybenzoic acid. So it is a peroxy acid, but we just write it shorthand because no one has time for that. Okay? So something to note, especially since you'll be tested on that particular one in organic 2. Okay? So then we're going to go to 34. So 34 says, which of the following reactions has a mechanism that involves the formation of a cyclic intermediate? Okay. So we want the formation of a cyclic intermediate. So we're looking, so our cyclic intermediate, so one that we know that's very common is we know the epoxide. We just talked about it, but looking here, there's no epoxide formation here. So that can't be the cyclic formation it's talking about. So chlorination of an alkane, we should realize that's a radical mechanism. We did have to know questions about the radical mechanism for exam 3, and we should know that that isn't a cyclic intermediate. That's a radical chlorine and an alkane reacting with each other one-on-one. So it's not going to be C. Dehydration of an alcohol. Dehydration of an alcohol is not adding things. Like our epoxide, when we formed our epoxide, it was because we took a double bond and both carbons simultaneously grabbed the oxygen. This is making the double bond. We're not using it to grab something and make a ring. So it's not going to be dehydration of an alcohol. And then we have addition of HBr to an alkene or addition of bromine to an alkene. What we should remember is that addition of HBr, one piece is going to react first, create a positive carbocation, and then the bromine is going to come in and attack the positive carbocation. So we're not going to use this one. It's going to be the addition of bromine to an alkene because we should remember that if I have an alkane that looks like this, and it's going to, like if we had a double bond here, and it's going to react, the first thing that happens is it makes this piece. So that's our cyclic intermediate. I know that we didn't do a lot of mechanisms in Dr. Hashim's class, but do remember that you are responsible for the radical mechanism, and then in organic 2, you're responsible for all of them. So keep that in mind. Mechanisms are very important. But I think, does anybody know, has Dr. Hashim posted her keyword list? Yeah? Okay. Yeah, so I think she narrowed it down from we learned 50 reactions a semester, so those of you that are in Dr. Hashim, you only need to know 20 or 25, whatever she put on the list. So use that list to study from. It's going to help you narrow down what you need to look at. All right, but the things that are on the list, know them well because she's giving you a keyword list, don't expect super easy stuff because she's telling you what to study. It'd be different if she's just oh, it can be anything. She'd expect you to know a little bit about everything, but because she's giving you a keyword list, you should know those things really well. Okay, 35. What is the major organic product of the following reaction? So we have a double bond here reacting with HCl. So we should know that HCl is going to go to the chlorine is going to go to the more substituted side. So when it goes to the more substituted side, we're going to get a chlorine over here, and the hydrogen is going to go to the other one. But we want to draw this out. So I'm going to draw this out as a line bond structure. So I have these two, this one, let's see, methyls, that chlorine, sorry, that carbon, this carbon, and there we go. So this is what it looks like, transferring from there to there. 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons. So we should know that we have HCl. This is why it's important for us to know the mechanism. HCl, this pi bond, is going to grab the hydrogen. It's going to give those electrons back to chlorine. So we're going to wind up with a hydrogen on the less substituted side, and we're going to have the positive charge here. However, our major product is going to be our most stable product, and that carbocation is going to rearrange because we're going to do a hydride shift right here. Because that hydride shift is going to put that on the tertiary. A tertiary carbocation is more prominent than the secondary because majority of it is going to want to resonate into the more stable structure. So that's what it's going to be. We're going to add in this chlorine attacking, and so we're going to wind up with our chlorine on the more substituted. So we're actually going to wind up with C because we're going to have carbon, 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 and then the chlorine's hanging off along with the two methyl groups. So that's going to be our major one because that reaction goes in that manner. So we should know how to resonate things. Okay? For those of you that had any trouble giving like the major product for reactions because you weren't doing resonance, that's something that you really want to be sure you're doing right in organic too, and it's something that can be counteracted by just knowing how the mechanism works. C. Okay. So here we go. What is the major organic product of the following reaction? All right, we have this CO3H. That's a peroxy acid. All right. That's a peroxy acid, but it's a peroxy acid by itself, so we're not making the anti-diol because we don't have anything to continue on. We said that this, which is also a lot of times specified as MCPBA, if we're using a specific one, it's going to make the epoxide. So that was chapter 14, something to note. All right, 37. What is the major product of the following reaction? So HBr, and it's specifying that there are no peroxides. 36 is B. It's going to make the epoxide. Okay? So 37, what is the major organic product of the reaction shown? So it's no peroxide, so we know it's the bromine's going to go to the more substituted side. We don't need to worry about resonance in this case because the more substituted side is a secondary carbon, just like its neighbor, so it's not going to resonate to another secondary, right? It's only going to resonate if it has a better choice. So secondary and secondary, equally good. So we're just going to look for the one that puts the bromine on this second carbon right here, which is going to be C. Yes. Puts the bromine right there. Okay. All right. Which of the following reagents cannot be used to distinguish between cyclohexane and cyclohexene? Okay, so this is definitely a question I can see Dr. Hashim putting on your exam. Why? Because something that she knows a lot of students were having trouble with, because if you guys didn't know, like me and her just like talk in her office a lot. So something that we talked about is that a lot of students were having trouble remembering, they remembered the reagents, but didn't remember the starting material that the reagent's supposed to react with. So people knew that Br2 added 2 bromines, but they didn't know they had to start with a double bond. So that's where a lot of students were falling into trouble. So this is one of those questions where we say, okay, do we know, can we connect the reagent to the starting material? Okay, so when we're looking at this one, we want to look, and it says which one cannot distinguish between cyclohexane and cyclohexene. So, if we're looking here, Br2CCl4. Okay, so Br2, we should know that when we have Br2 and CCl4, it's just going to be our, our solvent. But this isn't radical. There's no heat and light. So for this one, we need a double bond to react with. So if I had like 2 beakers, one that had cyclohexane, one that had cyclohexene, but I didn't know which is which, if I put Br2 in both of them, only one of them would brominate, the one with the double bond. So I'd be able to tell which is which. So this one can distinguish the 2 of them. So we're not going to go with A. Mm-hmm. You can use that same solvent for alkenes. Yeah, it's the pi bond, but they specify it with triple bonds because you like need it for triple bonds. Yeah. Okay, so concentrated H2SO4. Okay, so we're looking, so it's concentrated H2SO4, but in general, something we should know is that H2SO4, we can use it to make double bonds, but we can also use H2SO4 when we are trying to take a double bond and add an alcohol group and a hydrogen onto it. Now, it's not my favorite choice because I'm like, okay, we learned concentrated versus dilute, but for the moment, we're gonna like kind of mark this one as like we like halfway, like we think it will distinguish them, because hopefully if we put the acid into the double bond cyclohexene, hopefully we should see some alcohol groups being added, and regardless of concentrated or dilute, it's not going to react at all with something that only has sigma. Okay? Then we have KMNO4, all right? KMNO4, we can definitely, say, okay, we can distinguish them because we know that if we put KMNO4 into each of our beakers and we make them cold, one of them is going to create a diol. The one with the double bond, the cyclohexene, should react. Cyclohexane is not going to. So that can distinguish. We're looking for cannot. All right? And then this one here, we're looking at NaOH. All right? So we're looking at NaOH. And then we have never seen NaOH used on a alkane, but simultaneously, we have not seen NaOH used on a double bond. We've seen NaOH used to replace a halogen. We've seen that swap, but we have not seen just NaOH going and attacking a pi bond. Because remember, NaOH, that OH group is going to be negatively charged. I have a negative OH group. When we're adding alcohols generally to a double bond, remember, if we have a double bond, the first part is the double bond is going to reach out and grab something positive. There's no positive to grab here, so NaOH is not going to react with our cyclohexene and simultaneously is not going to react with our cyclohexane. So I put it in both beakers, neither one reacts. I don't have any idea which is which. So this is going to be the answer choice for 38. Okay? Then we're going to go ahead and do 39. What is the major product of the reaction shown? So the major product, we want to look here, and we're going to say, okay, BH3THF. We should realize that BH3THF is going to do like an anti-Markovnikov addition of water. So we're going to have the OH group go to the less substituted side. So my first thing I can get rid of is I can get rid of A, because it's putting it on the more substituted side, which we know is not going to happen. B and C have it both on the less substituted side, which is good. And D, we should hopefully know is not going to happen because it puts it on the complete other side of the ring, which is impossible. So then for us, it's determining which one of these it's going to be. We should remember that this hydroboration, or whatever, yeah, I think it's called hydroboration reaction. When we use BH3THF to add water, it's going to be a syn addition of water. So the OH group and the hydrogen group are going to be added to the same side, right? So for B, my added hydrogen went also on the same side of the ring. For this one, this is like an anti-addition. We want the syn addition, so it's B. All right, 40 says, which is the best way to synthesize the ethers shown? All right, so we just recently learned about ethers and how we want to, make them react. So we're looking at this. First of all, if we want to make this reaction happen, we need to look and we need to have the proper nucleophile in the proper group that's being attacked. So, looking here, first thing we should see is we should see option A. Option A has an alcohol group on one piece and an alcohol group on the second piece. So if they join together, you know, it seems like in our brains it'd be like, okay, well, one of the oxygens is going to stay, one's going to leave. But we should remember that OH is a bad leaving group. So these two are not going to react with each other because neither hydroxyl group is willing to leave to make the connection. So we're not going to have A as an option. All right? Then we have a negative oxygen here attacking this methyl iodide, or we have D, which is just the alcohol group and an iodide. So once again, if we want this reaction to happen, we need something that can attack and push this iodine off. An alcohol group is already fulfilled. It has what it needs. It's not going to be strong enough to form that ether because there's no negative charge. So we're looking for something strong. So we're going to get rid of option D. So these two are kind of opposites, B and C. We have our negative, like our nucleophile, we have it on the secondary for B, and then for C, we have it on a methyl or, you know, a primary. Okay? So when we're looking at what we want, so we need something negative, but we should remember that negative things, or negative nucleophiles, strong nucleophiles, are going to favor SN2, right? So when we think of SN2, we want our nucleophile to be strong. But simultaneously, we want our degree of carbon to be lower, right? Because primary is better than secondary for SN2, which is better than tertiary. And so here, this nucleophile can attack, this isn't even a primary carbon, this is just a methyl, which is even like the best possible, least substituted carbon there is. So here, it can attack a methyl group. For this one, this nucleophile is strong, but it has to attack a secondary carbon. So because we are using a strong nucleophile to form this, because we need a strong nucleophile to form this, we want to go with the one that is going to attack the lowest degree of carbon. So we would go with B because we want our halogen species, the one with the leaving group, we want that one to be the lowest degree carbon. So methyl would be the best choice for us to proceed by SN2. Yeah, C is also a methyl, but in this case, this is our nucleophile. We want our electrophile, or the thing that's being attacked. That's the carbon that we care about, primary, secondary, tertiary. So yeah, that was the difference between these two options. Okay, then we're going to go on to 41. So 41 says, which of the following acid-base reactions does not occur? So for us here, we can do ARIO. ARIO is something that works for us. So let's look here. In this one, we have a hydroxyl group and a carboxylic acid. So we're going to wind up with H2O and this thing here. We should know that for A, oh my gosh, carboxylic acid, that's probably the one that wants to act as the acid. So yes, this one will be favored and will occur because this one's more likely to act as the acid than water. So this way is what we're going to do. Okay, so this one can occur. Then we're going to look here. We have a negatively charged carbon, okay? So we should know that, we should know that water will act as either an acid or a base, but we should know that carbon really should never be negatively charged. It's very unstable, and it does not like being negatively charged. So this is definitely going to proceed because this carbon is going to get the hydrogen it needs. We're used to having hydroxyl groups floating around in solution. Negatively charged carbons are not going to be favored in solution, so this acid-base reaction is definitely going to happen. Same thing down here. This one, it's negative. We do not want a negative carbon, so this reaction is certainly going to go forward. This is kind of the opposite idea of the other ones. So this one, we have a negative hydroxyl group, but our carbon is fine. If this went forward, we would have H2O, and then we'd have C2H5 negative. And like I said, carbon is very unlikely to be negative. It's a terrible acid, so we're going to go with that. We could also look and just say ARIO and use ARIO to determine what's going to be the better acid, and we know that oxygen and nitrogen are going to be way better acids than carbon just based on the A of RAO, which is atom. Okay? And then 42. 42 says, when is oxymercuration demercuration the preferred method of synthesis of an alcohol? Okay, so this is like a terminology thing, but we should remember oxymercuration demercuration. And so oxymercuration demercuration, we should know, is going to give us the more substituted alcohol, right? Oxymercuration is going to be the one that's like HgOA2. It's going to be that one. So we know it's going to give us the more substituted alcohol. The question here is, like, which answer choice do we need to pick? So we look, the more substituted alcohol should be the Markovnikov product. So we can eliminate any answer choice that says we're going to get the anti-Markovnikov. So we can get rid of A, and we can get rid of C. So now we have two options. They want the Markovnikov product with carbocation rearrangements, or we want the Markovnikov with no carbocation rearrangements. So we have two options of making the Markovnikov product of a hydration. So we either use this method, which is like that, and then like NaOH, H2O2, or we use H3O+. We should remember, because she did mention it in class, we should remember that H3O+ will undergo carbocation rearrangement while oxydemercuration, mercuration, whatever, does not. It will not undergo carbocation rearrangement. Therefore, we would want to go with D. So we would want to use this when we want the Markovnikov with no rearrangement. So an example of this would be like if she gave you guys this, and she wanted this, and she gave you guys like options A, B, C, D of, different synthesis, like propose a synthesis where like A is like, 1, 2, 3, B is like 1, 2, all the different possibilities for synthesis. This would be one where she wants you to realize that H3O+ would rearrange and form the alcohol on the tertiary. So she could give you both of these. This could be option A, this could be option B. A lot of you guys are going to be like, oh, the alcohol group, it goes to the more substituted side. Circle it, I know this one. But this one will undergo carbocation rearrangement while this one will not. So something to keep an eye out for. Also, she has seen this final exam review, and she was like, I love it, use it. But it is very similar to hers in the format, just in the formatting, because I don't know if she told you guys, but your multiple choice is going to be A, B, C, D, not A, B, C, D, E. So it's just going to be like the 4 choices just like this, which means there might be less like throwaway options, I guess. So definitely know your stuff. All right, 43. What is the IUPAC name? Yeah. What is the IUPAC name of the compound shown? So first thing we should remember is that an alcohol group is going to be highest priority when it comes to naming our substituents. So we're going to want to put the alcohol group as number 1. Then when it comes between the methyl and the chlorine, it doesn't really matter. We just want to make sure that they have the lowest number possible. So to do that, we would want to go this way of 2, 3, 4. So we look here, we need to have 2,2-dimethyl, which we do. But we can get rid of B and A because they are putting the hydroxy here, which we should know that's going to be at the end of the name as an alcohol. Okay, because that's how we're naming alcohols, chapter 13. So we have our 4-chloro, 2,2-dimethyl, and then our options here are cyclohexanol or cyclohexyl alcohol. All right, this is just our vernacular. So we want to make sure we're saying cyclohexanol because that's how we're naming alcohols. You drop the E off of the end of cyclohexane, and you just add the -ol, okay? Let's go ahead and do 44. So 44, which of the following is least soluble in water? So solubility in water is going to come into play. We have a couple different bond types that we are going to use. All right, So we can have hydrogen bonding. We have London dispersion forces. All those forces play a role in whether things are going to dissolve with each other. But the main thing to come, to come to terms with is that like is going to dissolve like. So water is a polar molecule. Water has, has dipole moments, makes it a polar molecule. So we want to look for something that doesn't have that. Something that's not polar, something that has no dipole moments. And the only one we have here that has no dipole moments is going to be B, because B is just butane. Butane, it's just carbons and hydrogens. That's not going to create any sort of dipole. So it'd be like trying to mix like gasoline and water. They're very different. They're not going to mix. This one here can do hydrogen bonding because it's an alcohol. This one, it's going to have a dipole moment because of the oxygen, so the dipole moment is going to make it a little bit easier for it to go into solution. And then this is an acid, so it's going to break apart into its ionic form, and it's going to react with some of the water to create that and H3O+, so it's going to definitely dissolve. Okay. Move on to 45. What is the major product of the following reaction? All right, so the best thing for us to do here is to draw this out. So I have this group right here, and then it's HBr concentrated. So we want to say, okay, what's going to happen? So we look here. This is a tertiary, so even though we have HBr, it's going to happen by an SN1. So what's going to happen first is we have our HBr, and this oxygen here is going to take the hydrogen away from the acid so it can form a good leaving group, which will leave, right? And then we're going to wind up with this positively charged tertiary carbon. There's not going to be any rearrangement because it's positively charged, and it's on a tertiary, so that's the best it can be. So that bromine that's left in solution is now going to attack that tertiary position, so we're going to wind up with D. Okay. So we have that one, and then, all right, 46. Which of the following radicals is the most stable? So something just to note is remember that when we're talking about, radical reactions, we have two options. We have monobromination, monochlorination. And remember that when we do monochlorination, the chlorine can attach itself to any carbon because it can make a radical at any carbon. So we generally use radical bromination because that one is going to be more selective, and it's only going to put the bromine on the most stable one, which we should realize from doing the mechanism of monobromination is always the most substituted. So our most stable radical is going to occur where we would put the radical bromine, so it's going to be on preferably a tertiary, but then secondary, primary is going to be the order. So this one here is a tertiary, so that's the most stable. This is a primary, secondary, and a secondary. So those are not nearly as stable radicals as this tertiary one is. The reason monochlorination can put it on any carbon is because chlorine is going to react. It's more electronegative. It's going to react even faster than bromine. So even if it makes this radical right here, the chlorine can immediately swoop in and attack it and chlorinate that position. Bromine's a little bit slower. It's not as electronegative. So when bromine's making its way over to the radical, even if the radical's initially formed here, by the time the bromine gets over, this has already resonated and gotten itself to the tertiary position. Okay? We have that one. All right. And then we're on our last page, guys. I know, it's been a long day. So 47, talking about radicals now. So which of the following is an initiation step? So we want to look here, and what we should remember is we have initiation, propagation, and termination. So to initiate The thing we want to remember for initiation is we go from 0 radicals to 2 radicals. That's the big part, because to initiate, we don't naturally have radicals just floating around. So to initiate the process, we add that heat and light, and we split something apart into 2 radicals. Propagation is when we have, 1 radical and then like 1 non-radical, and we still end up with 1 radical and 1 non-radical. Propagation, we don't want to get rid of all the radicals because we're propagating it to keep going. We're making new radicals as we go along. And then termination is going to take 2 radicals and take us to 0 radicals, and that's going to end our process. So you can get a question on any of these steps. She can ask you, which one of these is initiation, propagation, termination, and you have to determine it. But we said here we want to go from 0 radicals to 2 radicals for initiation. So this is only a radical and a non-radical. This is, there's no radicals, and then we wind up with 2. So we should circle that one as our answer. But just to be thorough, we're going to look, and we have 1 non-radical and 1 radical reacting to form 1 radical, 1 non-radical. That's propagation. And then D, we have 2 radicals going to 1 non-radical, which would be termination. Okay? Then we're going to go ahead and we're going to do 48. So 48 says, which of the following reactions has an activation energy of 0? All right, so we're looking for something that has an activation energy of 0. So when we're doing that, first of all, the first one that we should be able to knock off completely is which option? Heard like one person say it, B. We should be able to knock off B really easily. Why? Because over the arrow, it says we're adding light. Light is energy. Therefore, that is an activation energy that is not 0. So yeah, we have to put energy in to make those radicals. So it should make sense to us that if we have to put energy in to make radicals, it's not going to take any energy for those radicals to just go back to their regular form, because it's something that's not normal. So we want to look for a termination step, because termination does not require energy of activation. So we're going to go with A, because it's 2 radicals that are just finding each other again and going back to the form that they're comfortable with. These 2 down here are propagation, so we're still making another radical. Every time we make radicals, we have a little bit of activation energy. So we're going to go with A for 48. Okay, 2 more, guys. So how many hydrogen atoms are there in the compound shown? So in this compound shown, we have to count all of our hydrogens. So we can look here and we can say we have 3 on this one, 1, 1, 1, 1, 1. This has 4 bonds already, so there's no hydrogens on this one. 3, and then 2. So if we count all of this up, it should come out to, I believe, 13. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But how many hydrogens? It's just one of those tricky things. Watch out for when they're not shown. All right. And then for question 50, the reaction of 1-butene with HBr in the presence of peroxide yields 1-bromobutane. The mechanism for the reaction involves, and it asks us what. So we've already kind of talked about this, but I have my 1-butene, and with peroxides, it's going to yield this one here, but it's asking for the mechanism involved. So we need to figure out what the mechanism is going to be. We're looking here, and just like with our normal one, right, without peroxides, the first thing that happens is that this pi bond is going to attack the hydrogen of the HBr. That happens in the normal one. We know the mechanism better for that one. So the alkene is going to attack the positive. Something that we can, first of all, keep in mind is look at our answer choices. The bottom 2, attack on the alkene by Br plus or H plus. All right? positive things do not attack, right? Positive things are going to be our electrophiles because they are what is attacked by the nucleophile. Nucleo means positive, phile means attracted to. So these are the electrophiles. They're attracted to negative things, but remember, electrons are like power, money. They're the things that are going to attack. So these two just aren't even right because positives do not attack. And then we look here, attack on the alkene by a hydrogen atom or attack on an alkene by a bromine atom. So we look at these two, attack on an alkene. All right, let's remember that even just, this is the peroxide mechanism, but even just thinking of the regular one, the bond is attacking the hydrogen, and then once we have a positive charge, the bromine comes in and attacks. The hydrogen doesn't do any attacking. Hydrogen never really attacks unless it's a hydride ion in like NaH. So that's not the case here, so B cannot happen, so our answer is going to be A. All right, so really quick for anyone that wants it, this should be, if you missed any of them, oh wait, it's not on there. Go here. So, everybody take a second and just do that. Okay, so I do have to pull this off. It will be up here because I have to put this little QR code thing. They really want us to encourage you guys. They want to know how to fix Study Union. I've been doing Study Union for about 3 years now, so we do take your comments and try to fix things. So I really encourage you on your way out to just do that. We have technically until 7:20ish, 7:30. And so if you want to come up and take a picture of this, you're more than welcome to. If you have any questions, you can come up and talk to me. Other than that, good luck on your guys' exams. I hope you guys do great. I'm sure you will. And maybe some of you next semester. Hi.
For number 10, I was like slightly confused because E and E, isn't that a double bond? And then Y and E is a triple bond?
Mm-hmm.
So why is it C then?
Because acetylene is just the name for a triple bond. It's like the common name, which so